A'udhu billahi minash shaitanir rajim. Bismillahir Rahmanir Rahim. Assalamu alaikum, my dear colleagues and my esteemed professors. My name is Zarar Salahuddin, and the topic on which I will be presenting is application of nanocomposites for CO2 gas barrier properties in gas pipelines. This is the outline of my presentation. First of all, let us go to the introduction. Corrosion is a very main problem which is faced in the industry as well as in domestic applications. And it poses a problem because of the fact that it compromises the structural integrity of the material to whenever a certain material comes in contact with gases which are corrosive, and they peel off the material in such a way that it will break down after some time. The amount of damage which is caused by corrosion is actually amounted by a certain degree, and we see that about 18% of all accidents which happen in the industry because of corrosion related problems. And this degree of damage which is caused is also having a financial loss, which is amounted to $589 million as according to a study carried out by NACE International. These figures show a certain gas pipeline which is in its normal form while it is transporting gas. But over time, the scaling, fouling, and other properties occur within the gas pipeline, which causes it to degrade, and ultimately, as you can see in the final figure, the pipeline breaks down and cannot function at all. Now, how to overcome this problem? In industry, most commonly, there are different types of coating materials used for this purpose. Different coating materials include asphalt, coal tar, as well as fusion bonded epoxy. However, as time has passed, new types of materials have come into the limelight. One of those materials which is currently under research is polymer nanocomposites. Why polymer nanocomposites are such an attractive material for use as corrosion inhibitors within the gas pipelines? That would be a very important question that can come to mind. Well, the one main reason is that it consists of two phases. One is the polymer, and the second is the nanomaterial or the nanofiller. Nanofillers are certain filler particles which have nanometer sized dimensions. At least one of that dimensions is nanometer sized, because of which it has enhanced properties as compared to a bulk material. Whereas the polymer phase of that polymer nanocomposite will give it the strength that is required. Many types of nanofillers have been used in research. Some of them include nanoclays, graphene, as well as very recently produced transition metal dichalcogenides, which have not yet been used for gas barrier properties. But as I will be explaining in the coming slides, these new materials are now coming into the limelight and can be used because of their good properties. Our work has focused till now on the use of a certain easily available polymer such as polyethylene terephthalate, and the use of hexagonal boron nitride as the nanofiller. The process that we used is, first of all, the synthesis of the nanofiller, then there was the synthesis of nanocomposite, and then characterization, and finally testing. The synthesis of nanofiller and nanocomposites is done by one method each. The synthesis of nanofiller was done by a process known as liquid phase exfoliation, in which solvent such as NMP, N-methylpyrrolidone, is used for the breakdown of bulk material into its individual nanosheets. This can be easily done by exposing or inducing certain ultrasonic waves onto the solution, which forms our nanofiller solution. And the second part is the synthesis of nanocomposites. Nanocomposites can be easily synthesized by a process known as solution processing. And solution processing is the method that we used. So first of all, we had the nanofiller solution. we combined it with a polymer solution, which we had formed, in which polyethylene terephthalate was mm, dissolved into the same solvent as used for the nanofiller synthesis. Both of these solutions were combined, and the final solvent solution was cast onto glass plates or petri dishes as we saw fit, and then finally the casted solution was dried and the nanocomposite was produced. This is a schematic diagram of how nanofiller is synthesized and how the nanocomposite is synthesized. Now, after synthesis comes the characterization process. For the characterization, we use three main methods: AFM, that is atomic force microscopy; SEM, which is scanning electron microscopy; and TEM, which is transmission electron microscopy. In the SEM, we can see that the flakes have about lateral dimensions of 0.5 to 1 micron. In the AFM, these results are further consolidated, and in the TEM, we can see that there are about 9 to 10 sheets in every flake, which means that the thickness of every sheet comes out to be roughly 3 nanometer, and the aspect ratio, which is the ratio of length and thickness, is about 331. The characterization of nanocomposites is the second part. Before the characterization of nanocomposites could begin, however, we had to look at the polymer, pure polymer membranes. And we can see that there are distinct and very visible pores on the surface of polyethylene terephthalate membranes, which are only blocked by a small addition of nanofiller, such as boron nitride. And furthermore, we can see from the XRD pattern that when there is no filler added, there are no such sharp peaks. However, even the smallest amount of inclusion of the nanofiller gives rise to certain peaks at characteristic angles, as can be shown by the XRD patterns. This shows that not only was the boron nitride assimilated into the structure, it stayed there and it maintained its crystalline nature. After the characterization was done, permeation testing and theoretical comparison of our experimental results was needed. For the permeation testing, we see that there is a very enhanced reduction of gas permeability on the inclusion of a very small amount, that is 0.01 to 0.2025 per weight percent of nanofiller. This reduction is so enhanced that it is not matched by, it is not closely matched by any of the models which have thus now been predicted. We checked the Nielsen model, the Bhardwaj model, the Kessler model, the Gusev model, but none of them were as close to predicting the permeability as our experimental results. However, at a certain increased amount of nanofiller, we can see that the Kessler model shows a certain degree of closeness to our experimental results. Therefore, we selected this model as our model of interest. Now, after what the work we have already done comes the work which we are to do. From the results which we have obtained for using polyethylene terephthalate and boron nitride nanosheets, we see that boron nitride nanosheet-like materials, for example, transition metal dichalcogenides, can be used as a nanofiller in the future. So we started doing literature review on it, and we found out that molybdenum disulfide and tungsten disulfide are two very good materials which can be used in future. Moreover, new types of polymers must also be studied, and we found out that thermoplastic polyurethane would be a very good candidate because of the fact that it is highly hydrophobic, and it would straight away eliminate the problems associated with water vapor, which is very much commonly found within the streams of natural gas which is flowing through the pipelines. So these are the two things that we have found. Moreover, preliminary synthesis and characterization has also been started on the nano sheets which are synthesized using molybdenum disulfide and tungsten disulfide. Furthermore, we would want to do the modeling, as we have already studied that models are very good way of predicting the behavior of any kind of system. So we want to see how our model, how we can develop a new model which will predict only our results in a very accurate manner. So this will also be carried out. Moreover, we also want to check the adhesion of our membranes or our nanocomposites on the surface of metallic materials, because this is our actual final application for which we are actually designing this nanocomposites. So this will also be carried out in the future. As a conclusion, I can say that hexagonal boron nitride nanosheets have been very successfully synthesized. Their inclusion into the polyethylene terephthalate membranes has been done, and it has given us very good results, which has encouraged us to look into other avenues as well. And for that, we have selected polymer as well as different types of nanofiller materials. And this gives us a very good way forward in which we can experimentally as well as through modeling find out different types of results which we can summarize in the future, and ultimately, inshallah, we will be able to include our membranes in the industry and at a larger scale as well. These are the references which I have used for the presentation, and thank you for your kind and very patient listening. Any questions from your side will be inshallah answered in the end.